should work.
I really don't know. Okay, let's try one of these. Okay. So this is VGA, so probably it's one of these. Let's try.
Shouldn't it be the first one because it's VGA1?
Oh, you're right. Right, box one. You're right. See? And maybe we have to do that again, so we have to... No, perché lui è collegato a... Sì. Quindi ora è collegato giusto?
Sì, è soltanto quello prima ci vuole adesso perché ha bisogno del suo tempo per svenirsi.
Perfetto. Perché l'avevo messo sul PC fisso, per quello forse c'è un problema, era quello.
È presente anche di 10.
Strano però hanno collegato questo qui, VGA 1.
Poi di lì fare un refresh del programma, cioè ritornare alla schermata iniziale.
Okay. Can you go back to the first one? Yeah.
Maybe
Try to exit.
And maybe refresh, maybe or stand by something.
Proviamo a staccare.
Okay, for instance, like restart the computer or something like that.
Aspetta. Perché se no gli possiamo usare sul computer fisso.
Se ci sono problemi magari la porta VGA con micro HDMI non funziona, sì.
No, niente quello oggi.
Però
Dopo avete anche la lezione voi? È obbligatoria quella? No,
dovrebbe essere un corso monografico.
Chi vuole
da
va.
scelta, sì, tra quelli da scegliere. Ma comunque mi spiace per gli inconvenienti di oggi. Io sento...
Qual è l'inconveniente?
No, nel senso
non c'è
che...
inconveniente.
No.
È che io... Sì, insomma è l'ora, quindi pensavo.
Sì, no, ma più o meno ci sono...
Però questo è l'unico inconveniente è che non ho... Io avevo capito che il Junior Club è obbligatorio.
Sì, però siccome oggi non c'è nessuno, a parte...
Perché non c'è nessuno?
Perché l'unica persona diversa c'è Gabriele Umbriano che ha avuto il problema.
Che ha avuto il problema che ha avuto.
Quindi non c'era nessun altro e quindi c'era... Cioè questo era un contributo esterno, no? E poi siccome c'era, tra l'altro stamattina ho avuto un inconveniente mio, nel senso che è arrivato la notifica che c'è il seminario giovedì.
Certo.
Questo ragazzo qui, giusto?
No.
Come no?
Il professore, cioè.
Ma non lo stesso, ha letto male.
Lui, perché si chiamano Andrea tutti e due?
Ha letto solo il primo nome, io
esatto.
allora ho visto male io, pensavo fosse la stessa persona con lo stesso seminario e quindi mi sono... Vabbè,
Vedi che
no, beh, grazie, ora.
Did you refresh?
Yeah, of course, yeah, but I don't have c'è un problema con
l'adattatore.
Me l'ha inviata
via mail.
Sì, via mail. Possiamo aprirla da lì e metterla di sopra.
Sì. Hai l'accesso a internet.
Allora, che devo fare per andare sulle mail?
Ah sì, no, scusa.
Webmail.
E quella studente UniPD?
Sì.
Vai su unipd.it. Webmail, login con
Non me l'ha mandata qui. Where did you send at which address? Do you remember? No. Because I think can you send it to appunto UniPD, giusto? Grazie mille. Ce la possiamo fare, non mi ricordo qual è, dovrebbe essere questa. Vediamo. Yes. Dov'è l'allegato? Ok, com'è? Non me l'avevano dato su. Ok, here we are. Ok. Come c'è quello sul...
L'hai salvato?
L'ho scaricato.
Ok,
sì.
allora vai su
Penso.
download.
Questo qua? Sì. Ok, perfetto. Sostituisci. Perché forse l'avevo già messo. E com'è che si chiama? Chiudi qui e qui. Questo giustamente abbiamo chiuso qua. Padova. Eccolo qua.
Messo in ordine? Sì.
Ole, we did it.
Io sto mandando in streaming.
Sì,
ok?
sì, ho
Dopo
già
mi fai
inviato.
mandare, per favore,
Sì, certo. E
quando siete a posto.
per metterlo su tutto schermo.
Dovrebbe essere questo qui.
Ok, so here you are. Sorry for inconvenience.
Just. So, hello everyone. My name is André Silva. I'm from the University of Lisbon, and I'm going to present. Okay, this is. It's not. Okay. Yes. Okay, this is better. So I'm from the University of Lisbon, and I'm in my last year of my master's degree, and I'm going to present you the work I've been developing along these years. So I've been my master thesis has been about galactic structure and developing a computational model to study it. So the title of this thesis is Tracing the Scale-Light Evolution of the Galactic Disk Using Open Clusters. Okay, so we know that in the universe we can find galaxies with different shapes, different inclinations, and this is the results from the Spitzer infrared for obtaining a Bolton fork diagram. And we have like spiral galaxies, elliptical galaxies, and irregulars. So we have irregulars here, spiral galaxies in this side of the graph, and ellipticals in that part. So we know that the Milky Way is more or less in this zone below because it's a spiral barred galaxy. Okay. So this is what the Milky Way should look like if we could take a picture of it from above. So it has about 4 spiral arms. It's what evidence shows us. It has a bulge, it has a bar in the center, and it's a spiral galaxy. Okay, so, but the problem is to study the Milky Way, it's really harder than studying any other galaxy, because to study it we must do it from the inside and not from the outside. So we have, from what we can see inside, we must derive properties like how many spiral arms can we have in the galaxy, is it elliptical, is it spiral, do we have a bar, how do we find all these things? Okay, so to understand these properties, the galactic structure and their properties, we need catalogs of objects. And these catalogs need to be as complete as possible, because we need to understand the difference of objects near the sun or more farther the sun, in different populations, in different ages, etc. So to study this, we need really, really accurate and precise measurements. And to obtain really precise and accurate measurements, usually people tend to use open clusters. Open clusters are just star clusters that live in the galactic disk. And why do you use like open clusters and not just field stars or any other objects? It's because since we have like a clump of stars, it's much easier to determine better parameters, for instance, distances, reddening, etc. And one thing that's really important is it's really hard to determine individual ages for individual stars and not for open clusters. So to study the evolution of the Milky Way, it's really, really difficult to do it with single stars. So we use open clusters to study the galactic structure. Okay, so to obtain parameters about the structure of the galaxy, we use the statistical properties of the objects. For instance, this work focuses on the scale height of the disk. Scale height of the disk is a measurement for studying the thickness of the disk. And this is obtained by using the vertical distribution of open clusters above and below the galactic disk as presented in this plot. So here we have Z, it's the distance from, it's the height from the galactic plane that ranges from minus 400 to 400 parsec. And on the y-axis we have the density of open clusters per unit of length. In this case, just parsec. And we have, this is the distribution of open clusters for different ages, which isn't important for now, but it's just so the scale height is just given by the distribution of open clusters above the disk, which follows a Laplace distribution, and this parameter here gives us then a measure of the scale height. Okay, and the center of the distribution, which isn't exactly zero, gives us a displacement of the sun from the galactic plane, which is given by this parameter here. For instance, we can see that different objects in the galaxy define different scale heights. For instance, field stars have a scale height of 300 parsec because they are more dispersed around the galactic plane, but when we consider open clusters, we only have 80 parsec of scale height because they are more close to the plane. If we consider, for instance, giant molecular clouds, they are even nearer the plane, which define a scale height of only 50 parsec. Okay, so what's interesting about this distribution of heights is that when we increase, when we divide the open clusters in different groups characterized by their ages, for instance, we have divided this catalog in 4 groups, different group of ages. So one is the young clusters with ages below 200 million years. Then we have the intermediate clusters or intermediate young clusters with ages between 200 and 450. And we have the intermediate old clusters which have ages between 400 and 1000 mega years. And then we have the old clusters which define ages above 1 giga-year. So we observe that the scale height of the older populations is higher than the scale height defined by the young population. And why does this happen? Well, in the literature, many authors have proposed different mechanisms to try to explain why these open clusters have a larger scale height than the younger. And these mechanisms have been proposed, for instance, like heating of the disk, so or radial mixing, which is increasing the height of clusters by encounters with objects like giant molecular clouds or etc. And they would gain energy in those interactions and reach higher heights, which with time would find higher scale heights. That's better. That's better. So maybe this happened, and those interactions gave energy enough to reach higher heights. Or maybe we know that during the history of Milky Way, there was some merging with satellite galaxies, and maybe this scale height comes from high altitude clusters that we got from those satellite galaxies, or maybe we have some different conditions in the primordial disk of the Milky Way that we don't know about. But the problem here is that most of these properties do not happen in open clusters, because the dynamics of open clusters are not the same as individual stars. So if we have two stars and they interact, they will change their energy. But if, for instance, we have a collision of an open cluster with a giant molecular cloud, it will not gain any energy. It will, for instance, interact and will lose mass via the collision, will lose energy, and the possibility is it will eventually dissolve. So this may explain only a little of these increased scale heights, and is not enough to explain all the differences. So the proposed model for this thesis is just, if we notice, we have that the range of the scale heights doesn't really change with the age. So if we had radial mixing or heating of the disk or whatever, we would expect this range of heights to increase. So if we have stars at 400 parsec, with time we would expect to have some at 600 or 800 or wherever. And we don't see it, we just see it a little more thicker here, but it's just different scales, so it all makes sense. So we have same range of heights, and probably what is happening is just, we know that open clusters tend to suffer from more dissolution effects near the plane. So what would eventually happen is these clusters here would dissolve much faster than any other clusters who are born farther from the disk. So this distribution of clusters near the plane would start decreasing, and then artificially we would see these scale heights increasing, but it's not that they are moving away from the plane or anything else, it's just we are losing the open clusters that are more close to the plane. Okay, so to test this model, I have built a computational model that is based on that open clusters have orbits around the galactic plane. That's that can be approximated by an harmonic oscillator movement, more or less, movements of the open clusters around the galactic plane. And then what we do is just when the or not, and see what we get from the simulations. So the simulation, the algorithm, is pretty straightforward. We just the Milky Way potential. After updating the height, they may or may not find a giant molecular cloud. So if they find a molecular cloud, they get dissolved. If not, they don't. And so we repeat this until we meet the simulation time equivalent to the evolution time of the Milky Way, and see what results we obtain. So to generate star clusters, we must generate it with a certain scale height that's also given by a Laplace distribution with a certain Bert scale height. this parameter is usually related to the scale heights defined by open clusters, because since they are young, they haven't suffered yet dissolution in the meantime, and so the scale height defined by the young population should be the birth scale height for open clusters, although it's not exactly the same, because if we have, when open clusters are born, they are born at a certain height, and then they start moving towards the galactic plane. So when we observe open clusters, on average, we observe them with a less scale height than they were actually born, because on average they are closer to the plane than the heights they were born. So this value is a little bit higher than the scale height defined by open clusters, and we have the dissolution of open clusters, because the main dissolution effect for dissolution is giant molecular clouds. We just use probability for dissolution according to the scale heights defined by giant molecular clouds. Okay, so the parameters that are important for this simulation are it's the birth scale height, the amplitude of encounter with giant molecular clouds, that basically tells us how many clusters survive after the simulation, and then the dissolution scale height, which tells us if we want to dissolve more clusters near the plane or more farther away. Okay, so simulations in the parameter space for the probability of encounter and the dissolution scale height for the different age groups show us that, as we expect, for young clusters the problem is totally degenerated, because since it's so little time, they do not have time to change their scale height, so any parameter works for obtaining this. But when we consider intermediate populations of clusters, we see that we have this region that any value can be okay for the simulations. And this fits really well, except for the old clusters. Yes?
Can you explain what the colors are?
Okay, so the colors here in the graph, it means the relative error from the so we simulate, we run the algorithm, and we obtain a scale height for the different groups, and we compare these obtained scale heights with the scale height from the catalog. And so if we have a lighter, more white color, it means that the simulation has gotten a good result, and if you have a more red color, it means that the simulation parameters are more farther away. So we observe that the good parameters are in this region for the intermediate clusters, and for the old clusters it's up here. So this doesn't mean that the model doesn't work or anything else. What is happening here is that we know that we have selection effects in the catalog, because old clusters on general have already suffered evolution, dynamical evolution, and lost many stars during their lifetime. So they are not, in theory, they are not as bright as young clusters. So when we observe open clusters in the sky, we are biased toward discovering more young clusters than old clusters, because they are old and they get confused against the background, or we just don't have enough resolution to see this faint object. And so we know that we are missing a lot of open clusters that are old near the galactic plane, and that artificially will increase the scale heights of the catalog. So we know that it should be a lower scale height, and when, for instance, we have observational data from Gaia, we'll see that this curve will probably decrease a little bit and will improve the results from the model. Also, this is the curve that represents the scale height in terms of the age of clusters. So the dots correspond to the data from the catalog, and this field curve represents the obtained for the simulations for the best fit. So we observe that the model can almost perfectly fit the whole data, except of course for the older clusters in the catalog, for the same reasons of completeness of the sample. So comparing the results from the simulations to the results in the catalog, so if we compare the scale heights, they are basically the same. So young clusters in the simulations define a scale height of 51, that's the same for catalog. Intermediate clusters define a scale height of 57, 58 in the catalog, it's within the error bar. The same for intermediate old clusters, and the only difference is here in the old clusters because, okay, same reasons. And we have done this including different range from the sun to compare the catalog. So we have 1 kiloparsec, 1.75 kiloparsec, and 2.5 kiloparsec from the sun to see the differences in the statistics and completeness. And we see that every time we run the simulations, it's always within the error bars. So this model appears to work and appears to be good to explain why that's the open clusters at higher ages define a higher scale height than the young populations. Just to mention, the only problem the model is facing right now, and it's the next step I am working on, it's that the sample size, the number of clusters that we have in the simulations, when compared to the number of clusters that we have in the catalog, we get a lot, really a lot of old clusters when compared to the catalog. And this is because I am generating open clusters all with the same mass. But we know that the lifetime of an open cluster is probably related with their initial mass. So when I introduce an initial mass function for the clusters, only the most massive clusters will survive through time, and this will solve the majority of open clusters that are accumulating in the most high ages. Okay, so in summary, the model is able to reproduce the catalog just by simulating a really simple model, okay? And the other, also there are many surviving clusters in the older populations, okay? Introducing an initial cluster mass function, which is in progress, should then resolve this problem. Also, future work will include introducing, okay, the initial cluster mass function is already in progress, introducing initial velocities for the open clusters to see kinematic signatures of the sample. Also, considerations about 3D galactic potential, because we know that the Milky Way potential may vary with latitude and longitude, and may be different in different parts of the galaxy. And also using Gaia Data Release 2, that now will have much better data, so we can build a new catalog of open clusters with much more accurate and precise results, and then we can use it for better estimation of the parameters in our simulations. Okay, and that's all. Thank you.
you have a model with some limitations that
Yes.
you are trying to amend, and you have a catalog of open clusters, which is what it is.
It is what it is.
Yeah, I wanted to ask a bit more about the input catalog. What are the limitations of the input catalog that you can eventually take into account to get a better comparison?
So the limitations is we know that the catalog suffers from incompleteness from certain distances from the sun. So if you use the catalog, for instance, only clusters up to 1 kiloparsec of distance, we know that it's more complete if we use a catalog up to 2 kiloparsec, for instance. So we can, one of the things I have done is divide the catalog for different heliocentric distances, so we can test the different results for lower distances and for higher distances. So in lower distances, we expect to have a more complete sample, although we are also reliable on the statistical fluctuations of the sample because it's a small distance. If we compare with a higher distance in the catalog, we have a better statistics, but also we have a more poor completeness of the sample. So we have to play with this trade-off in a low distance and in a high distance.
Other questions? So let's thank Andy again. This is everything for today. See you next Monday. Can you wait a second? I have to say. You are in streaming, so you have to be, if you want to sign the authorization.
Okay.
Do you have a pen?
I think I have it.
Oh, thank you.
No, I don't.
No, okay, so I'll find one. Un casino perché c'è solo lui, quindi non so come gestire. Ora se Piotr mi dice qualcosa stampo il foglio ve lo faccio passare su non so. It's a special journal, special one, really, really special. If you have to sign, I will pass with you. You are next to me, so you. Thank you. Okay,
What
so
do I write here?
no, this is not important. Just okay. I don't think just the two sign here, one and one here.
1 year in a
Yeah, that's important. Maybe just put the city where you come from and the state. This is not for me. I don't really.
Okay.
Because usually it's okay.
What else?
I don't know. I really don't know. Okay, so maybe the state and place and date of birth.
State.
Yeah, and
like,
I think this is important. The
Ah,
institute,
okay.
yeah, that's the one important. Because usually it's for us PhD from here. So no sign today. No. I will pass. I will come to you if we have to sign something. Okay. I will come and back upstairs with the sheet. Okay, so I will find you, no problem.
She will come in.
Yeah. But I don't think there is need to sign something today. So no, I will not. So thank you so much. Cosa? È la liberatoria per lo streaming. Perché siamo in streaming. Mi spiace per oggi, ma c'è solo.
Cosa è successo oggi?
No, di tutto di più.
Dimmi cosa è successo
No,
oggi?
vabbè, alla fine abbiamo risolto però.
Come è andata in Cile?
Bene.
Dove sei stata?
A Santiago.
No, alla SIA o a Paraná?
No, Viete Paraná.
A Paraná.
Sì. Ma tra l'altro ieri mi hanno accettato un talk a Santiago per cui sono super di fretta perché il 12 febbraio riparto un mese e
E
mezzo.
vai a Paraná?
No, Paraná stavolta no, però ho un seminario, cioè un seminario.
Vai un mese e mezzo usa una visitorship, una cosa
Sì,
così.
perché esatto, perché sto lavorando con una ragazza in Cile,
Chi
con
è?
Alice Zurlo.
Ah certo,
Ok,
sì.
perfetto.
Quindi è la Diego Portales.
Esatto.
Ho capito, bene?
E quindi mi hanno accettato un talk in una conferenza giù a Santiago che c'è la prima settimana di marzo e colgo l'occasione per tornare a lavorare con
Cos'è la conferenza sulla
diversi
vita,
spunti.
diversi spunti.
Quindi torno con la scusa, diciamo, di chiederle a
Noi qua?
il volo e basta, poi sì, perché il resto poi mangiarsi nella borsa. Sì, non l'università, è in Università.
Sono stato dal 18 dicembre al 2 gennaio.
Questa
E a outra coisa foi, quando tu chegaste ao aluno, estão a ver, realmente, isto é um rei de aumentar. Mas uma coisa que a Bela se diz, e também que dá
Io sono andato varie volte, sono più cariche che sono
não se diz ter a conversa. Realmente, isto é um rei de aumentar a produtividade. Portanto, não se dá para a natureza material como nos não falar. E as pessoas aí não estão assediadas. Tu tens que criar as pessoas no nome delas devem haver tu és o que é.
sì, la
Mas quanto mais fácil fazer uma coisa